In this video, I will discuss about quantum entanglement and Bell states, and also I will show you that how you can create an entangled states using real qubit by IBM Q. Now, transfer of quantum information between two distant quantum particles without any type of connection, that is teleportation process, cannot be possible without the entangled particle or entity. Entanglement is a very interesting phenomenon. After receiving the Nobel Prize by Alan Aspect, John F. Clauser and Anton Zeilinger on the quantum entanglement in 2022, the news has been flashing in the news channels, papers, magazine, social media, etc. After that, people have been getting more and more curious about the quantum entanglement, teleportation process, and quantum information processing. Now, if you go through the dictionary, you find that the lexical meaning of the entanglement is a complicated or compromising relationship or situation. That is, so the entanglement is basically strong correlation between two or more particles or entity. Let's understand its concept in a very simple way. Suppose you place an order, a burger and a bun to a bakery shop. Let's understand its concept in a very simple way. Suppose you place an order, a burger and a bun to a bakery shop. Delivery boy delivered it at your home within a packet. Now this is the packet. You can see here. After receiving the delivery, you unpack it very quickly and find that there are two same identical packets in the box, and you cannot distinguish them, which one is burger and which one is bun. So to make sure, you have to open a packet, one of them, and after opening a small packet, you first find the burger. That means it is fixed that in the other packet you will find the bun. So opening any packet fixed that what is in the other packet, that is, they are entangled or correlated with each other. It is a rough and outline idea to understand the entanglement process. But quantum entanglement is not so simple. Here, placing your order has fixed the food and the style of the packing by identical box has created this correlation, that is the entanglement. Suppose the bakery shop offers variety of combo offers in a fixed price and you tell them delivery any one of them which will be available. Then after the delivery, you cannot specify after opening any one of the box what will be the other one. So in this case, they are not entangled. So to create entangled particle or entity, you need a specified operation which I will discuss later. Now discuss another example about the entanglement. Here you can see two particles spinning in the clockwise direction if and only if you and your friend looking at the same angle or same direction. And if any one of the particle changes its states, that is the spin, from clockwise to anticlockwise, another particle changes its spinning accordingly. It is the basically entanglement. That is, if one particle changes its spin, another also changes its spin. Now, I can said earlier that the two balls are, that is the two particles are spinning in the clockwise, but only when the angle of view is same as your friend. But if you change your angle of view, that is direction of view, then now you can see, if you see at the left side particle, you find that particle is spinning clockwise, and if your friend looking at the right side particle from the opposite side of your viewpoint, he will find that the particle spinning anticlockwise. So you can understand the process of measurement or reading the information is a vital point of quantum entanglement. Now, if the spinning of any one of the particle changes from one state to another state, that is the clockwise to anti-clockwise, and other will not change accordingly, the particles are not correlated to each other, that is they are not entangled. Okay, so here you can see one is clockwise, another is anti-clockwise, showing that. Now again come back to the first example. In the first example, anyone open the packet consisting of burger. From any angle or any side, it will always be a burger, and other packet it will be a bun or otherwise. But in second example, when you and your friend looking at the particles in different side or angle, the result is different. So measurement is a vital part of the entanglement. And in quantum world, time is another factor, that is the output of the measurement may be different in different time. Now I will discuss about quantum entanglement using the quantum particle. Consider the horizontal vibration as the ket 0 or ket h, and the vertical vibration as quantum state ket 1 or ket v. Now consider two quantum particles having the horizontal vibration put in a box, that is a closed system. Now you can see the particles in a closed system in the horizontal vibrational mode. These particles in the box goes through a operation which operates on the particles and create the entanglement. This shows that something operates on these particles which is within the box, and this is the operational circuit which can create the Bell state, and the Bell state is actually the entangled state. So after this operation, ket 0 0 and ket 1 1, or can say ket h h and ket v v state will be generated. That is the state of the output circuit is ket 0 0 plus ket 1 1 by root 2, or horizontal position plus vertical position by root 2, which I will represent it by two box, and the probability of having these states are 50% each. Now these two boxes are showing two different states whose probability of having the state horizontal vibrational state is 50% and the vertical vibrational state is also 50%. Clear that after operation, if we open this box, there is a 50% chance to get ket 0 0 or horizontal vibrational state in both particles, both are in horizontal vibrational state, and 50% chance to get the particles in ket 1 1 state, that is both are in vertical vibrational state. If one in the horizontal vibrational state, other will be in the horizontal vibrational state. If one in the vertical vibrational state, then other will be in the vertical vibrational state. Now here you can see the particles in the box, that is 50% chance to get in horizontal vibrational mode and 50% chance to get in the vertical vibrational mode. if both the particle in the same box. Now I will show you what will happen if you separate these two particles into different boxes. Now these are two boxes where the particle will be transferred. Now this is the way the particles is transferred into different boxes and they kept in a distant apart. Now if you and your friend wants to measure states of the particle within the boxes, if you wants to know the state of the particle within the box, you cannot determine without opening any one of them. So here the particle may be in the state horizontal vibrational mode or vertical vibrational mode, or this one may be in the horizontal or vertical vibrational mode, that is either in Ket 0 state or Ket 1 state, or here also either in Ket 0 or Ket 1. So these two particles kept in a distant, and these two particles are also BF random, but they have a relation between them, that is they are entangled. Now let's see what will happen if you open the box. Now see, after opening the box by you, your friend also follow the same process of the opening the box in the same direction and the same style, and you both see that the particles in the vertical vibrational mode. Now in the another set of particles, if you follow the same process of the opening, you may find the horizontal vibrational mode. Here, as these two particles entangle to each other, so when one particle in Ket 0 state, other particle also in Ket 0 state, and if same particle is in the Ket 1 state, the other also in the Ket 1 state, which is shown by the horizontal and the vertical vibration of these particles. If you measured these particles in different way and you don't tell your friend how you are measuring, then you may find the random output state, and you cannot say whether the particle is in entangled or not entangled state. So let's see. Now if you look at this side to measure or to see the particle, then you will find that this particle is in the vertical vibrational mode, and your friend will follow the other measurement process, other opening process as the previous one, and he finds that the particle is in horizontal vibrational mode, and change the point of view, or and you change your direction of looking, the measurement is also changed. So without the same process of measurement, you cannot say the particle is entangled or not in entangled state. So to understand the entanglement process, you should in your mind that quantum entanglement is a bit delicate. In quantum world, you and your friend could measure the same particle, and yet you will not get the same information until you get together and share your readings or information. However, you together find that you can get more information from the measurement than you individually is not possible. Thus, quantum entanglement goes much further than the perfect correlation. Now go to the IBM Q interface where I will show you how to create an entanglement state using the Bell circuit. Now put here a 0, here also 0, and put a Hadamard gate here, and put a C0 gate here, and this is the measurement for 1, and this is the measurement. So here you can see two possible state, which is gate 0 0 and gate 1 1. Now reduce to 2 qubit system, which make you more understandable. So here you can see the probability of getting 0 0 state is about 51%, that is about 50%. The probability of state getting the probability of getting state 1 1, gate 1 1 is 48.6, that is about the 50%, but theoretically it is the 50%. So now inspect the circuit. Now first one shows this is the 0 0 state. Now Hadamard operation is done, which creates the superposition state, and now C0 operation, or using this visualization or using this Q sphere, you can see that there is two different state. There is created superposition. There is created two different state with having the probability 50%, is gate 0 0 and gate 1 1. Now if you run through the simulator vector, state vector, now the process is completed. This is the output. See more details. So see, this is the output of this circuit. Okay, here frequency is 543 and here the frequency 481. That is the probability of getting 0 0 is 53%, and here the probability of getting 1 1 is 47%. And this frequency means measurements have done on 1024 sorts of measurement. In these 1024 sorts, 0 0 outcome is about 543 and the 1 1 outcome is 481. Now let's see how the real quantum computer output looks like. I have already have an output of real quantum computer as if you run this one in the real quantum computer, it will take about 5 to 6 hours or many more, or be less than that. That's why I have already run this circuit on IBM Q Manila. Now see, yes, now see in the IBM Q Manila, this is the output of the real quantum computer. Now see, as I have used 4 qubits, that's why there are 4 different possible outcomes are here, where 0 0 is 453, that is 44%, and the probability of getting 1 1 is 49%. But there are also two different states, is 0 1 and 1 0. Also there is a chance to get these states, that is the gate 0 1 state is about 1.7%, and there is a probability to get 1 0 state, it's about 5%. Okay, now so here you can see that there is 0 0 and 1 1 state is more and more dominant. So here so real quantum computer create Bell state, and here you can see when one qubit is in 0, then also the other qubit is in the 0 state. And if one qubit in gate 1 state, one qubit is in gate 1 state, then the other qubit is also in the gate 1 state, and this is actually the entangled state. And you know the measurement is very vital for any quantum system. And in the next lecture I will discuss about the entanglement state and discuss about the different Bell states and the different Bell state circuits. Thank you for watching. Please subscribe this channel for more and more videos.